welcome back to lectures on advanced calculus for engineers, and this is lecture number 10 of module 1, and in this lecture I will be talking on higher order partial derivatives. So here we have the content, partial derivatives of higher order. So we have already gone through the partial order derivative, so first order partial derivatives, and then there will be some worked problems. Well, so the first order partial derivatives of f, which was discussed already in the previous lecture, is basically keeping all other variables or treating all other variables as constant and differentiating the function with respect to the variable of interest. So for example, here if you want to get the partial derivative with respect to x, in that case the y coordinate here will be treated as constant. So here we have substituted already y naught, and there is a variation in x naught plus x to this x and divided by x, and this quotient we are looking for the limit. If this limit exists, we call it partial derivative with respect to x, or the first order partial derivative with respect to x. Similarly, the partial derivative of f with respect to y was defined, and there also we had a similar argument that x naught will be kept as constant, and then we have variation in y. For example, here as we define this ordinary derivative with respect to one variable. So y naught plus delta y minus this here f y naught divided by delta y, and then we go for this limit, and if this limit exists, we call it that the first order partial derivative of f at x naught y naught exists. Now in continuation to this, so we will generalize the idea for the second order or for the higher order derivatives of f. So for instance, we have this del over del x of del f over del x. So we are again differentiating the first order derivative. We have here the first order derivative of f with respect to x, and then we are differentiating again. So once again, so it's a second order partial derivative of f with respect to x, and this is the notation which we use f and in the subscript x x. So it is the meaning here is the 2 times partial derivative with respect to x. We also denote it by this symbol del 2f over del x2 or del x square. Here we have again the first order derivative with respect to x, and then we are differentiating with respect to y now. So here we have differentiated second time also with respect to x, but now for instance here this function del f over del x we are differentiating with respect to y, and the symbol which is used here for this second order partial derivative is f y x, or we also denote by del 2 f over del y del x. In the literature you will find that some authors denote here like del 2 f over del x del y. So it is just a matter of symbol how you define, but the meaning is clear here that first this partial derivative with respect to x, and then we are differentiating with respect to y. Similarly, we have here the partial derivative with respect to y, and then again we are differentiating with respect to y. So again 2 times the second order partial derivative with respect to y. This is denoted by f y y, or we also denote it by del 2 f over del y 2. Similarly, first here the partial derivative with respect to y, and then partial derivative with respect to x. So there is a difference here. In this case we had the partial derivative with respect to x, and then we have differentiated with respect to y, but in this case now we are differentiating here with respect to y first and then with respect to x. So there is a difference in the order. So this is denoted by then f x y, or with this symbol as per our notation del 2 f over del x del y. So here first with respect to y and then with respect to x. So these partial derivatives f x y and f y x are called mixed derivatives. Let us go to the problem directly, because we have already the idea, we have the definition that how to get the partial derivatives of first order, and here it is a matter of fact that we will be differentiating 2 times. So, for instance, we want to compute this del 2 f over del x del y at the origin of this function f x y. So, the function is defined for x y not equal to 0 0 as x square y over sine 2 x minus 3 y over x square plus y square, and when x y is 0, the value of the function is 0. So, to get this second order derivative, that means del 2 f over del x del y, meaning that we will be differentiating del f over del y once again with respect to x, right. So, this we treat now like a function. So, this is the short notation, we already used this f y. So, this is the partial derivative with respect to x of which function f y. So, this is the partial derivative with respect to x of f y. So, what as per the limit definition, what will be this partial derivative with respect to x? So, we have to have the limit where delta x will go to 0 at the end, and our function is f y now. So, f y, and we are talking about this derivative at the origin 0 0. So, here since we are taking this derivative with respect to x, so what will happen here, 0 plus delta x, and the second argument will be 0 minus f y and 0 comma 0 and divided by delta x. So, what do we have basically here? We have the limit delta x to 0 and f y, that is the function which we are differentiating with respect to x, and then we have delta x comma 0 minus this f y 0 comma 0 and divided by delta x. But now in this evaluation, what we have observed, that we need to get this f y, the partial derivative of f with respect to y at this point delta x comma 0. Also we need here the partial derivative of y, partial derivative of f with respect to y at origin 0 comma 0. So, these two terms we have to evaluate separately, and then we will substitute here and find out this limit, that will be the second order derivative of f. Well, so this is what the, as per the definition, we have this function f y, and this is the variation in the x. So, 0 plus delta x and comma 0, the second argument will remain as it is, because we are differentiating with respect to x, and divided by this delta x. So, to get this limit, we need to have this f y delta x 0 and also f y 0 comma 0. So, these two we have to separately compute. So, this f y delta x comma 0, again we will apply the definition for the partial derivative with respect to y. So, the partial derivative with respect to y of f, again, so this will be the limit delta y to 0, because we are talking about the derivative with respect to y, and then there will be a variation in the y. So, the delta x will remain as it is, because here this is the point delta x comma 0, and here we have 0 plus delta y and then here 0 and divided by delta y. So, this quotient we have to evaluate, and now this f delta x delta y from the function. So, that will be delta x square, then we have delta y, we have sine 2 delta x minus 3 delta y and divided by this delta x square plus delta y square. This is the term f delta x comma delta y, and when we have f delta x comma 0, because there is a argument here, second argument 0, and in the function there is a product x y. So, that will become 0. So, that is minus. So, minus this 0 and then divided by the delta y, and then we will look for the delta y goes to 0. So, this delta y and this delta y will get cancelled, and when we set delta y to 0, what will happen? So, this term will vanish and delta x square, then delta x square will go, and this term will also go. So, at the end we will get sine of 2 delta x, sine of 2 delta x. So, this is just the f delta x delta y over delta y, and as we have just evaluated. So, at the end we will get sine 2 delta x. And similarly for this fy at 0 0, which is rather simple, because one of the argument in each case it is 0, and in the function we have that product in the numerator x into y. So, both will be 0 and then minus 0 divided by delta y. So, this limit will be just 0. So, now we can substitute in our definition here for the second order derivative fy delta x 0, we have already, this is sine 2 delta x minus 0 over delta x. So, this limit reduces to sine 2 delta x over delta x. Well, so this is the limit which we need to compute now, sine 2 delta x over delta x. So, as delta x go to 0. So, here we see that it is 0 by 0 form. So, we can use the L'Hopital rule. So, here we have cos 2 delta x and then we have 2 there and over 1. So, limit delta x go to 0. So, this delta x goes to 0, that means cos 0 will be 1 and the answer to this limit will be just 2. So, we have evaluated this partial derivative with respect to y and then with respect to x, and the answer to this derivative is 2. So, this was simple. So, there was no new idea involved as such. We have just this definition of the derivative, which is used already for the computation of partial order derivatives of order 1, and here the same definition is used 2 times basically. So, we have used here first and then in fact here the second time and the third time to compute this higher order derivatives. Well, so coming to this problem number 2. So, we have here both the mixed order derivatives we need to evaluate. So, del 2f over del x del y, del 2f over del y del x for this function, and we will realize that these two mixed order partial derivatives, in fact in this example itself, that they are not the same. So, at one point if you compute this partial derivative del x del y or del 2f over del y del x, then it may happen that you have two different values. So, that we will demonstrate here, and then there is a sufficient condition under which these two derivatives, these two mixed order derivatives become equal. So, here let us first compute this del 2 f over del x del y, that means del over del x of del f over del y. So, again we apply this the definition for the partial order derivative of order 1 indeed here, just f y is a function now. So, that as per the definition you will have f y delta x comma 0 minus this f y 0 0 over this delta x. So, again we need this f y delta x comma 0, also we need f y 0 0. So, we need to compute those now. So, as per the definition again f y delta x 0. So, with respect to y we are computing. So, we will have the argument here 0 plus delta y and this is 0, and delta x will remain as it is, and then division by this delta y, and this limit for delta y goes to 0. So, when we substitute there this f delta x delta y and minus f delta x 0, because this is going to be 0. So, at the end we have just f delta x delta y, which is delta x delta y, then delta x square minus this delta y square over this delta x square plus delta y square, and then in the division we have also delta y, and at the end this delta y goes to 0. So, this delta y and delta y will get cancelled, and when we take this limit delta x delta y go to 0. So, this will become 0, this will also become 0, and we have here only delta x. So, that is what we have written here, that delta x. So, f y at delta x 0 is simply delta x, and this is this f delta x comma 0, that is 0. So, with this anyway we have got this delta x. Now, this f y 0 0. So, f y 0 comma 0. So, we have f 0 delta y and f 0 0 over delta y, both of them here are 0. So, 0 minus 0 will give you 0. So, that is the value here, and then we will substitute in the definition at this place. So, this is delta x simply, and then you have minus here 0 and divided by delta x. So, delta x gets cancelled again, you have 1. So, the limit for this is simply 1, and now we will compute the other partial. So, by changing this order of the differentiation. So, that means now the partial derivative with respect to y of partial derivative of f with respect to x. So, that means this f x will be differentiated partially with respect to y. So, as per the definition of the limit, we have here f x, and with respect to y. So, we have the variation in the y argument. So, delta y, so 0 plus delta y minus this 0 over this delta y. So, now in this case we need this f x 0 delta y, also we need f x 0 comma 0. So, these two quantities are required now. So, in this case, so f x 0 comma delta y as per the definition with respect to x. So, we have delta x to 0, we have delta x here and the variation in the ith place. So, 0 plus delta x and minus 0. So, this we can easily compute again. So, delta x delta y, that is delta x delta y, and this case here we have delta x square minus delta y square over this delta x square plus delta y square, and then divided by delta x, and at the end we will be looking for delta x goes to 0. So, this delta x gets cancelled, and now this time we have to take now the limit as delta x goes to 0, and here this delta x and delta x gets cancelled. So, when we set delta x to 0, so this will be 0 and this will be 0, and then we will remain with delta y and then minus delta y square, and then we have here also delta y square. So, this time we will get with minus sign as delta y. So, the answer for this limit will be minus delta y, and similar as we have done before, the f x at 0 0 now, because in both the arguments, both the functions here, one of the arguments is 0. So, this will also become 0 and this will also become 0, and in that case 0 minus 0. So, the value will be 0. Now, we can substitute here in our final limit. So, we have minus delta y minus 0 and then divided by delta y. So, this delta y and delta y gets cancelled, and then we have minus 1, the limit of this del 2 f over del y del x. So, what we have observed that in our when we have computed this del 2 f over del x del y, the value was 1, but now del 2 f over del y del x, the value is minus 1. So, both the values are different, and this is in general. So, but under certain restrictions we have that we have the result that these two values will be the same. So, what is that result here? The equality of mixed partial derivatives. So, the theorem says that if f x, f y, f y x all exist in the neighborhood of that point x naught, y naught. So, here we have taken f y x, and also the second condition is that f y x is continuous. So, that continuity is actually important for this f y x, and if this is the case, then f x y will also exist at that point and both will be equal. So, this is the result. That means that if this one of them, we can replace here x y, and then we will say that f y x exists. So, if one of them exists, and then we have this condition also on f x, f y, and this f y x, they exist in the neighborhood of that point, because we are talking about continuity. So, the existence in the neighborhood is also important. And then, so if this f y x is continuous basically at that point, then the other one will also exist and the value will be also equal. This is what the result is. In general, what we also say, because these are sufficient conditions, so we also say that if the mixed order derivative, this f y x and f x y, they are continuous, suppose in an open domain D, then at any point x comma D in D, this f x y will be equal to f y x. So, for the equality of this these mixed order partial derivatives, the continuity of these derivatives, these second order derivatives is important, and under those these continuity conditions, then we have the values same. So, let us move to the problem number 3, and here we need to compute again f x y and f y x for this function. Now, the function is x y cube over x plus y square, and this is naturally when x is not equal to minus y square, elsewhere the value is 0. So, if we compute first this del 2 f over del x del y, that means the partial derivative with respect to x of this function f y, then as per the definition we have f y and delta x minus this f y 0 over delta x. We need to compute this, and what we observe, because here again we have this product and 0 is present in all the in both the functions. But before we go to the substitution here, this is not the function directly, we have to have this f y first. Yeah. So, we have to compute this f y and this f y at 0 0. So, let us do that. So, f y at delta x comma 0, what we have, because with respect to y. So, we have delta y to 0, we have delta y there, we have the variation here in the y coordinate, and delta x remain as it is. So, here we have f delta x and delta y minus f delta x comma 0 divided by this delta y, and delta y goes to 0. So, this we need to compute then. So, we have delta x and delta y cube over this delta x plus delta y square, this is the term here, minus because of this 0, that will be 0, and then we have delta y. So, this delta y and this delta y cube will cancel, we will have a square there, and at the end delta y go to 0. So, what we realize when delta y go to 0, because delta y square is sitting there, so this will become a 0, and similarly for f y 0 comma 0, because we have 0 delta y, we have 0 comma 0, and both of them are 0. So, this will become also 0, and now we can substitute back to this limit there, and what we will observe that 0 minus 0 divided by delta x, this is 0. So, the this mixed order derivative del 2 f over del x del y is 0 in this case. Now, we compute the del 2 f over del y del x. So, del 2 f over del y del x, we have now del f x over del y, and then as per the definition. So, with respect to y means we have the limit delta y goes to 0, and the limit here we have this delta y, the variation will be also in y. So, delta y and minus 0, the first argument will be as it is 0. So, we need to compute this f x 0 comma delta y, we have to compute f x 0 comma 0 to compute this limit. So, this f x 0 comma delta y as per the definition. So, we are talking about f x. So, we have delta x to 0, we have delta x, and then the variation will be there in the first argument, and the second will remain as it is. So, delta y and delta y. Well, so in this case now, earlier it was 0, but now we will check. So, we have here delta x and delta y cube over, we have delta x, we have delta y square. So, this quantity minus this 0 and then divided by delta x. So, delta x will get cancelled, and then we have here delta x to 0. So, if delta x go to 0, this go to 0, we have delta y there. So, the answer for this limit will be delta y, not 0 like in earlier case. So, we have delta y here, and f x 0 comma 0 as usual, because when we apply this definition, both the arguments, both the functions there, the 0 will be one of the arguments, and then that will be 0 minus 0. So, again 0. So, now we substitute here into this definition. So, we have delta y minus this 0 over this delta y, and then this is equal to 1. So, it was 0 there, and now we have 1 here. So, these two partial mixed order derivatives are not equal. So, what we can definitely say that since these two are not equal, we can claim that this fxy and fyx are not continuous at 0 0. Why? Because if they are continuous, suppose they are continuous, then these fyx and fxy must be equal, but they are not equal. So, with this we can definitely say that fxy and fyx, these two functions are not equal or are not continuous at this 0, 0 point, because these derivatives are not equal. And we can check this continuity in fact, and we will see that indeed these functions are not continuous. So, just to check, to confirm that this fxy and fyx are not continuous in this case. So, for that what we need to compute? We need to compute fxy and fyx at non-zero point, non-origin point. That means with taking this function xy cube over xy square, we will compute the derivative. So, we will compute the derivative where x is not equal to minus y square. We can easily compute that. Just this is a nice function, and direct computation of the derivative can give us the expression for fxy or fyx. So, in this case the fx x comma y, so the derivative of f with respect to x at point x comma y, where x is not equal to minus y square. So, at this point we the usual definition of the derivative, what we have, the here the denominator a whole square, and then we have x plus y square, and then we take the derivative of the numerator with respect to x. So, y cube minus the numerator as it is, and the derivative of the denominator with respect to x, and we will get 1. So, here we have xy cube and here also xy cube, we can cancel it, and we will get here y power 5. So, 3 plus 2 5, and then x plus y square whole square. So, this is the value which is written here. So, we can simply differentiate this one with respect to x, and this is the derivative wherever x is not equal to y square. Similarly, we can differentiate this now with respect to y. So, this function here will be differentiated with respect to y, keeping that x constant. So, again this quotient rule for the derivative we can apply, and then what we will get? We will get y power 6 plus 5 x y 4 over x plus y square power 3. Well, and then so this is also wherever x is not equal to minus y square. So, we got this derivative fyx at xy, and this is also interesting and easy to check that in this case when we have x not equal to minus y square, because we have this nice function xy cube over x plus y square. So, at all those points fxy will be equal to fyx, because there is no issue about the continuity and all, everything is continuous, all these derivatives are continuous also at those points. But the problem is at the origin which we are addressing here in this question. So, this evaluation we have done, we have the second order derivative for all those points where x is not equal to minus y square, and now we take that limit to 0 comma 0. So, from this x not equal to minus y square, we will move to the origin and see whether what limit we are getting. So, to take this limit, if we choose just this path x is equal to my square, so that will take us to the origin, and in that case what we realize when we substitute this x is equal to my square, we have 1 plus 5m there and m plus 1 whole cube here. So, this limit depends on the path, the limits depend on m. So, therefore, we can claim that this limit does not exist, because from this x not equal to minus y square, if we want to go along this x is equal to my square path to 0 0, and in that case we realize that this the limit depends on path. So, for example, you take x is equal to 2y square. So, along this path of course x is not equal to minus y square in any way, and then you substitute there in this function and take the limit as x goes to 0, we will realize that we get a number there which is again different. If you vary here this coefficient, instead of 2 if you take 3, then you will get another number. So, it is depending very much on the path you choose to approach to 0 comma 0. Therefore, this limit does not exist, and hence we cannot talk about the continuity of f x y or this f y x. So, indeed in this case these functions f y x and f x y are not continuous, which we have already observed, because f x y and f y x at 0 0 were not same, because if they are continuous, those values must have been same. So, this is the last problem we will discuss in this lecture. So, here we will show the existence of second order partial derivative, though the function is not continuous. So, that is also an interesting example where we have already discussed this, the connection between the continuity and partial derivatives, and in general there was no connection as such, but here also we will observe that in fact this function is not continuous and second order partial derivatives exist. So, not only the first order, but also the second order partial derivative exists. And just to show that this is not continuous, we will take a special path y is equal to x cos x and see that what is the limit here when we approach to origin. So, x y goes to 0 0, this one, and now along this path we will obviously this path will take you to the origin. So, we will just set here limit x to 0 and substitute y is equal to x cos x. So, we have here x cube cos cube x over x minus cos x, and we are interested in this limit. So, 1 x will get anyway cancelled. So, we have here x to 0 and there x is square, we have 1 plus cos cube x over this 1 minus cos x. So, this limit we want to evaluate, and we know how to evaluate, because as x goes to 0 we are getting this 0 by 0 form. So, we have to apply this L'Hopital rule at least 2 times, and then we can get this limit easily, and this limit comes out to be 4. So, this when we take f x y, this limit as x y goes to 0 comma 0, in that case we realize that limit is 4, but the function is defined as 0. So, this function is not continuous obviously, and then we will be talking about now the partial derivatives, and we will see in this case that the second order partial derivative or derivatives in fact they exist. So, just we will evaluate here f x at 0 0 for instance. So, f x at 0 0 as per the definition, we have the delta x go to 0 and we have f x delta x comma 0, f x 0 comma 0, we have divided by delta x, just this quotient, this limit will be evaluated now, but for that we need again this f x delta x 0 and also we need f x at 0 0. So, again this first order partial derivatives at delta x comma 0 and 0 comma 0 point is required. So, let us compute this f x at this point x comma 0, and as per the definition. So, x plus delta x minus this x over delta x, and the 0 for y will remain as it is. So, to compute this, now we have f x plus delta x. So, f x plus delta x means x plus delta x cube, there we will write, here the y will be 0, and then here also we have x plus delta x and y will be 0. So, this is this function, then minus we have f x 0. So, there we will get x cube over x. So, that means x square, and then we have delta x and the limit also delta x goes to 0. So, in this case, so this also have a square there, and what we have x square. So, x square will get cancelled, we have 2x delta x and then plus this delta x square term will be there, and we have delta x. So, as this limit delta x goes to 0, we have just 2x there. So, this limit is 2x, and this f x 0 comma 0, when we have delta x comma 0 minus f 0 0. So, f 0 0 is 0, and here we will evaluate this, and this is also coming to be 0. So, having this in hand, we will substitute this there. So, we have 2 times delta x minus this f x 0 0 is 0 over delta x, and this value is 2. So, what we have observed that the function is not continuous, but is still those partial or even higher order partial derivatives, second order, third order, they may exist. So, there is absolutely no direct connection with the continuity and the existence of partial derivatives, which we have already observed in detail in the previous lecture. Well, similarly, we can also evaluate like f y y at 0 0, and with the similar arguments what we have before. So, in this case, this f y 0 comma delta y will be like minus 2 y, because of this minus sign, that minus 2 y will come, and then f y at 0 0 will be 0 again, and after substituting into this limit, we will see now this is minus 2. So, we can evaluate f y y at 0 comma 0 as well. Well, just to conclude this, so we have learned then how to compute the partial derivatives of higher order. So, mostly all problems were on second order derivatives, but we can again further move to the third order or fourth order, and the process was which we already followed for the computation of first order derivatives. So, there was absolutely no new observation here, only we need to apply the definition, that limit definition, to get the derivatives again and again. What was also important, that the continuity of these higher order derivatives f y x and f x y, if they are continuous, so that implies that f y x will be equal to f x y, otherwise in general these values are not equal. Well, so these are the references we have used for preparing this lecture, and with this I thank you for your attention.